Hi everyone, and welcome to lesson 4 of Unit 4. And in this lesson we're going to kind of go directly from our last lesson about calculating concentrations and use our knowledge of concentrations to help us actually prepare some solutions. And we are going to give you very specific steps for preparing solutions, and these are very important laboratory techniques that you're going to be expected to know how to do in grade 12 chemistry, but also for any of you doing a university chemistry course. So being able to accurately, very accurately prepare a specific concentration of solution either from a solid, so here's an example, where you're preparing it from a solid sodium hydroxide or from a concentrated liquid. So oftentimes you'll be given a concentrated amount of acid and you're going to need a much lower concentration for the experiment. So we're going to learn the two methods of preparing solutions, both from a solid and from a concentrated liquid. Now, one quick aside before we get into the lesson is that you're going to see some textbooks and some videos refer to something called molarity. Now, molarity is actually the same thing as concentration. And so your textbook uses the letter capital C to indicate concentration, and we know that concentration is given in moles per liter. So concentration is the number of moles divided by the volume in liters, and so that's the letter. Most textbooks, or a lot of textbooks, use a capital M to indicate concentration. So technically, the molarity would be given as 0.01 M. Now, you can see why this would be confusing in our textbook, because we use capital M to represent the molar mass. So we have that symbol that we use for the molar mass. But I want you to know that if you ever see a capital M relating to solutions, it does in fact mean moles per liter. So technically, molarity and concentration are the same thing. Okay, so I'll just put a little note here that says same thing. Okay, so if you ever hear the term molarity, really they're meaning concentration. Okay, so here we go. Let's get going with today's lesson. Preparing solutions. So for part A, we're going to go over the steps required to prepare a standard solution from a solid. Okay, and then I've also included a little video, because normally I would walk you through how to do this as a laboratory technique, and in the video they'll walk you through these steps. But basically in this little example where we write out the steps, we're going to use the example of if you had been asked to prepare 500 milliliters of a 0.25 mole per liter solution, in this case of sodium chloride. Now again, I can't emphasize enough that you need to be extremely accurate. When you're given this task, you can't, the expectation is that you're not going to come back to the lab bench with, at the end of it with 0.5 or 0.253 or even 0.254. The expectation is you're going to come back with exactly 0.25 moles per liter, because being inaccurate will have dramatic impact on some experiments, and in particular one that we do in this unit is a titration. Okay, so here we go. Let's get going. Step number 1. So as soon as you've been told to prepare a certain solution, and picture yourself being in grade 12 chemistry and you've been asked to prepare this particular solution, the first thing you're going to do is pull out your pen and paper and do some calculations. So first of all, you're going to calculate the mass of solute that you need. So in other words, in this case, the mass of NaCl. Okay, because you're going to go and you're going to get the solid NaCl, and we're going to have to figure out how much we need. Well, we've been given the volume that we want, 500 milliliters. We've converted that to liters, and we've been given the concentration of solution we want. So we're going to do the two-step process. So first of all, we're going to say, well, the number of moles we need is 0.25 moles per liter. That's my C, times the volume, which is 0.5 liters. That's my V. And when I do 0.25 times 0.5, I get 0.125 moles. So there we go. We've converted to moles. And then what we'll do is we'll calculate the mass we need. So the mass is equal. We've just calculated the moles. It's 0.125 moles times the molar mass. And so we'd go and we'd say, well, let's do the molar mass of NaCl. We'll go to our margin. And that would be 22.99 for the sodium plus 35.45. And there's only one of each in sodium chloride. So we'd get 58.44 grams per mole. So we'd go here and go 58.44 grams per mole. And when you multiply those, you get 7.305 grams. And it looks like we've got two significant digits. And so we'd say, I'm going to go and get 7.3 grams of this. Okay. All right. So the next thing, so you've done your calculations, and now your job is to go into the lab. So step 2 is you would obtain the calculated mass. So you're going to use an electronic balance, an electronic scale, or an electronic balance. And so you'd go to the back of the lab and you'd get the sodium chloride bottle and you'd measure out the 7.3 grams. Okay, then what you do is you're going to transfer this mass into the into a volumetric flask, also called a round bottom flask. Now, these flasks are very specifically designed for this process of creating a solution. I'll just show you them. Here's what they look like. They're these skinny necks on them, and there's a different size depending on the amount of solution that you're making. So in this particular case, we're making a 500 milliliter solution. So in this case, I would pick this one right here. I'd go to the cupboard and you have all different sizes. I'd pick this size. All right, so that's the volumetric flask. I would get a piece of paper or a little a funnel that I could put the mass in. I would dissolve the solute in a small amount of distilled water. So I would go to my flask and I would put some distilled water in here and fill it up maybe halfway. And then I would put a little stopper in the top of my flask, and then I'd shake it up. And so I'd try to get all my solute to dissolve. You don't want to do this at the end. You're going to do it again at the end to mix it up, but you also want to do it at this point to try to get that solute to dissolve. Okay. And then what you're going to do, so step 3 was to transfer it to the volumetric flask. Step 4 was to dissolve the solute in a small amount of distilled water. Step 5 is here's the critical step. And this is the most important thing to maintaining your accuracy. Well, it's not the most important. Certainly getting the correct amount on your balance is important. But here you've got to fill the volumetric flask up to this etched line. What I mean by that is all volumetric flasks have this little etched line in them, and you can see them. I know it's kind of They're very accurately put on there so that if you fill the water up to that etched line, you will have exactly, in this case, 500 mils or 1,000 mils, 250, and so on. So that etched line has been calibrated so that they know when you filled the liquid up to that point, then you have exactly 500 mils of the solution. Okay, so you're going to fill it up to the etched line, and then finally you're going to stopper the flask one last time. You're going to invert it, put your thumb on top of the stopper so the stopper doesn't come out. You're going to invert it a number of times to ensure that all of the solute has been mixed around and you've got a nice consistent color, and if it is colored, or a nice consistent amount of the solute everywhere in the solution. Okay, so these are the steps. These are the steps that you would go through as a chemist to prepare a very specific 500 milliliters of a 0.25 mole per liter solution. Okay, and there is a video. I show it. I've included it with the lesson. There's a video that you would walk through, and it's gonna show you that method. Okay. Part B then today, so we've gone over how you would prepare a solution from a solid. Well, now we're going to go over how you would dilute a solution. In other words, how you would prepare it from a more concentrated solution. But before I do that, I'm going to just go over a new formula with you, and then I'll take you through the steps. But I want to take you through this formula first. So this formula right here is what we call the dilution formula. And you can see it says C1V1 is equal to C2V2. C1 is the concentration of your initial or stock solution. And so this is the more concentrated solution. So I'm going to say here the more concentrated. So it's the bigger number, more concentrated. Okay. And V1 is the volume of that initial concentrated solution. C2 is the concentration of the final, or what we call the dilute solution. And V2 is the final amount, or the final volume of that dilute solution. Okay, you will often see, sometimes people will write it with different subscripts. They'll write it like this, and you'll see why. Instead of doing C1, they'll often write C with the subscript C, meaning the concentration of the concentrated solution. And then this one would be V with a C, so VC, volume of your concentrated solution. And then C2, they'd write CD, so the concentration of your dilute solution, and VD, the volume of your dilute solution. So just so you're aware, sometimes you'll see it written like this, CCC, let me just fix that up a little bit, CCVC is equal to CDVD. So there are, either one of those is correct. I just wanted to show you that. Okay. Well, let's try these in a problem, because you can see that it might get a little confusing because there's two concentrations and two volumes present. Okay, so how would you make 350 milliliters of a 0.2 mole per liter solution of sulfuric acid from an 18 mole per liter solution? Okay, so I want you to notice right off the bat that you've been given three different things here, three numbers. So look at this. I've given 350 milliliters. Now I'm hoping you guys will recognize that that is a volume. And the way you recognize that is based on its unit. Milliliters are a unit of volume. So there we go. I know it's a volume. How would you make 350 milliliters of a, and then look at this, a 0.20 mole per liter solution? Well, you'll recognize that mole per liter is a concentration. Okay, so I've been given a concentration, a solution of sulfuric acid from an 18 mole per liter stock solution. I'm going to put a little comma in here to show you that I've got different things. And finally, again, this one's also moles per liter, so hopefully you're going to say concentration is 18 moles per liter. Okay. The key then to using the dilution formula is making sure you know which of these go together and also understanding what's required. So I want you to notice here that in this particular case, obviously whichever one of these concentrations is the larger number is the more concentrated one. So notice that obviously 18 is a lot higher than 0.2, so this one is my C1. It's my concentration of my stock solution. Okay. Well, that by default then, that this concentration is my C2. It's my concentration of the dilute solution. Now, what about that 350 milliliters? Is it the volume of is it V1 or is it V2? Well, notice that in these questions, these two go together. It says, how would you make 350 milliliters of this? Those two are together. So this is actually the volume of your dilute solution. And clearly what's missing is your V1. In other words, how much of that 18 mole per liter solution do I need to make this 350 mils? Okay, well now that we've kind of identified what we're missing or kind of what we've been given and required, we'll write the formula out. So C1 V1 is equal to C2 V2. And I'll plug my numbers in. 18 times, I don't have V1, so I'll just write V1. And then C2 is 0.20, and V2. Now, this is interesting. Do I need to switch it to milliliters? Well, in a question like this, where you have the same units on both sides, you don't have to switch it. You can leave it as milliliters, but just know that your answer will also be in milliliters. So just be aware, I'm going to leave it as milliliters. You can switch it if you like, and it would be 0.35 liters. But in this case, I'm going to leave it, and I'll just know that my final answer is going to be in milliliters. So to get rid of the 18, this is my substitute and solve now. I'll divide 18 off this side, and I'll divide 18 off this side. And so my final V1 in this case is 0.2 times 350 divided by 18, and I get a really small number of 3.8 milliliters. Okay, so you just do 0.2 times 350 and then divided by 18, and it's 3.8 repeater, and so I should round that. I'm just going to fix that up. I should round it to 3.9. Okay, so the question I'm just going to address here is that's how much of the stock solution you need. So I'll just say here that's the amount of the 18 mole per liter solution you need, solution needed. Okay, but where does the other 350 mils or the rest of that come from? Well, what I'll tell you is that, and I'm just going to put it in a different color, you will also need 350 minus 3.9, which is equal to 350 minus 3.9, which is 346.1 milliliters of distilled water. So just be aware that in these dilution questions, you often don't solve for the actual amount. You can, obviously, by doing this little extra step. But this amount is not technically, that 346.1 milliliters isn't in your C1, V1, C2, V2 calculation, but they expect you to know that the remainder of the distilled or of the dilute solution is just water. So in other words, look at this. You measure out your 3.9 milliliters of the 18 mole per liter solution, and then you're basically going to add in 346.1 milliliters, and that will bring you up to the 350 that you wanted. And that new solution will have this very weak concentration to it. I'm going to go over those steps in a second just so you can see them, but let's do another one here just to practice using that dilution formula. So here we go. In this case, it says 25 milliliters. I'm just going to write down here given. Well, I know I've been given a volume because milliliters is a volume unit. So volume, 25 milliliters of a 6 mole per liter solution. Okay, well, I know that that's a concentration. I don't know whether these are C1s or V1s or C2s or V2s yet. I'm going to try to figure that out in a minute once I've read the question. So 25 milliliters of a 6 mole per liter solution. Now, hopefully you guys see how that these two things are connected. So they're either both going to be C1 and V1, or they're going to be C2 and V2. 25 milliliters of a 6 mole per liter solution of nitric acid is diluted by adding 125 milliliters of water. Oh, this is interesting. Okay, so my next volume, if you add 125 milliliters of water, it means that my next volume is going to be 150 milliliters. Notice what I did there. There's a little trick because I've added this amount to the 125. Okay, what is the new concentration? So our required is a new concentration. Okay, well, let's double check. Then I got to put 1s and 2s here. So do you agree that by adding water, I'm going to make it more dilute? Okay, so that means that that one is the 2. It's the dilute. Because remember, I remember up here that dilute, V2 is always dilute. It's always the dilute volume. So that V2. And so clearly, I'm trying to figure out the concentration of the new one, or the dilute one. So these ones are both C1 and V1. They're the concentrated values. Okay, so here we go. Let's use our formula. C1 V1 is equal to C2 V2. Let's plug our numbers in. So we've got 6 moles per liter times 25, and I'm going to leave it as milliliters, but I know my answer will be in milliliters, is equal to C2 times 150. And then I get rid of the 150 by dividing 150 off of both sides. And so my C2 is going to be 6 times 25 is 150 divided by 150. Oh, good. It's going to be 1 mole per liter. Okay, so just be aware of that's that's how I use this dilution, these dilution concentrations. Okay, and volumes. Okay, well, let's return to our problem. So let's say you were asked by your lab instructor to prepare a standard solution. I apologize. It shouldn't say from a solid solute. It should say from a stock solution. Okay, so how would preparing a standard solution from a stock solution? So in other words, how would you prepare 250 milliliters of a 0.01 mole per liter solution from a stock solution of 0.25 moles per liter? So notice that, again, you've always got to go down. So my stock solution has always got to be more concentrated than my new dilute solution. So clearly 0.25 is more concentrated than 0.01. It's a smaller number, but you can't go the other way. Okay, so here we go. Just like we did with the in the first part, we have to start step 1 by doing some calculations. So here we go. I know that I've got a C1 of 0.25 because it's the concentrated solution. And I know that at my C2 is 0.01. That's the dilute concentration that I want to prepare. And I know my V2, I want to prepare 250 milliliters of it. So I've got a C1, a C2, a V2. Okay, so there's my formula. Let's sub and solve. So 0.25 times V1, I don't know how much of that one I need, is equal to 0.01 times 250, and I'll leave it in milliliters, and I know that my answer will be in milliliters. So V1 is going to be equal to 0.01 times 250 divided by 0.25. I'll plug those numbers into my calculator, and I get 10 milliliters. So what that's telling me is that I need 10 milliliters of the 0.25 mole per liter solution. 10 milliliters of 0.25 mole per liter solution. Okay, well, what will the remaining, so wait a second though, my final answer is 250. So I'm going to need, you will also need 240 milliliters of distilled water. So the distilled water is what's diluting it. You'll also need that. Okay, so here we go. Once again, we're going to go grab a volumetric flask, and you're going to half fill it with distilled water. What I'm going to emphasize here is the whole idea here, the reason for having this step in, and I've written it in my hand here, is that normally what you're doing when you're diluting is you're diluting acids. And the reason why you put the distilled water in first is that you always add acid to water. You don't go the other direction. And so that if we had put this 10 milliliters of highly concentrated acid into a solution and then poured water on top, you can get a very dangerous reaction. So you always put a little bit of distilled water in the bottom of your flask. I say half fill, but as long as there's some in there. So again, in this case, I would have went and grabbed a 250 mil, there it is. I would have grabbed that one in this case, the 250 mil volumetric flask. I put a bit of distilled water in it. And then what you're going to do is you're going to measure the required amount, of concentrated solution using a pipette. Now, in the video I'm going to include with this lesson, it's going to show you the process. But let me just show you what a pipette looks like. These are these long, skinny tubes, and they're used to give you very accurate volumes. That's, the fact that they're so thin gives you this accurate volume. And there's the bulb that you use to suck them up with. And the video will show you this. Okay, so you use a pipette to transfer the concentrated solution. So in our case, this was the 10 milliliters into that volumetric flask. You're going to transfer the solution to the required volumetric flask. Then you're going to add more distilled water. The remainder of that 240 milliliters, you'll add that in up to the etched mark in the flask. Remember, that etched mark is very critical. You're going to stopper it just like you did the first time, invert it several times, and now you'll have your new solution. Okay, so here it is, and again, I will have, this is the, I show you the video here, but I'll also include it in the lesson on D2L, but there's a short video that will walk you through how to do a dilution using exactly these techniques. Okay, well, that's about it. There's some problems here to practice using the dilution formula. So on these ones, you're going to be C1, V1 is equal to C2 and V2. And just remember, the ones are the concentrated solutions and the twos are the dilute solutions, and just figuring out which is which. And then here are some homework questions on page 324, which are just going over kind of what we just did, sometimes going from a solid, sometimes going from a liquid. All right, good luck with that, you guys.